All right, folks. If I wanted to know, let's say we don't have internet. Let's say internet is down, so it's like a regular Tuesday here. And I want to know something. I want you to go write a paper about Lincoln, Nebraska. Tell me everything you need to know. I need to know about Lincoln, Nebraska. Okay. Where would you go to do that? We don't have the internet. Okay, so you go to the library, you go to the encyclopedia. Okay. What else in the library could you use? No internet. Would an atlas tell me something about Nebraska? Okay. Encyclopedia. What kind of books are those things called? Okay, so we do have the internet. You go and you write a paper about Lincoln, Nebraska, using all these things on the internet. What are those things called on the internet? What is the last page that you write using maybe MLA format? References, right? Okay. So that's the encyclopedias, atlases, thesauruses, dictionaries. Those are references in the reference section of a library. Okay. Because you look at those to tell you something about a topic of interest, right? Okay. Up here at this angle 146, alpha. I'm not going to deal with 146. I don't like 146. 146 is kind of the Lincoln, Nebraska to me. Okay. What am I going to reference or look at to tell me about that 146? What do you mean? What do you mean do 90? Which would give me 56, right? So here's my question then. If you're going to do that, that would mean that if I'm in the right mode, I'm in degrees, that the sine of 146 would be the same as the sine of 56. And we see that those are different. Okay, so what I'm going to reference is its supplement. So what we're going to do here is we're going to look at that angle, okay, which in this case would be 34 degrees, right? So the 34 degrees is going to tell me everything that I need to know about 146, okay? That 34 degree angle, or that red angle that we have drawn up there right now, that is referred to as a reference angle. It's going to tell you what you need to know, okay? And what happens is if I were to take this angle, this terminating ray, and reflect it back across this y-axis, okay, can you argue, because I did a reflection, that that angle right there is going to be the same as this red one? Okay, so that means the sine, the cosine, the tangent of this blue angle is going to be the same as the sine, the cosine, and the tangent of this red angle, except for the signs, the SIGN, the plus or minuses, okay? And therefore, the sine, the cosine, the tangent of the blue angle will be the sine, the cosine, and the tangent of that angle of interest, except for the plus or minus aspects, okay? And all students took calculus concept will help us remember what trig ratios have a positive return and which ones have a negative return. Okay, so that's kind of what we're going to get into today, talking about something called reference angles. We've already been dealing with this the last couple of days, but I never used that terminology. Now I'm going to use that terminology as we move forward. All right, so this is the structure. Like if you get 100% stuck or confused with what we're doing, or how to work a particular problem, this is kind of the safety net of way of doing it, okay? I'll give you some shortcuts as we go through this. The way I think about it, I'm not saying the way I think about it is the right way, but it works, Okay? But it says a reference angle. The way that we deal with a reference angle, we first let theta, the angle of interest, be an angle in standard position. That means our starting, initial ray has to be the positive x-axis, and then our terminating ray is going to move counterclockwise and terminate somewhere else in the coordinate plane. Okay? So the reference angle, which we are going to denote with the theta and a bar over the top of it, that's referred to as theta bar. Okay, theta bar. So the reference angle theta bar associated with theta is the acute angle formed by the terminal side of theta in the x-axis. And all that is saying is that in order to do what we're about to do, you are always, wherever your terminating ray stops, you're going to draw a vertical line back to the x-axis. Okay? Okay, you're always going to draw back to the x-axis. What we did at the beginning, when we said we were going to draw, essentially did this scenario here where these two values were different, that was drawing a horizontal line back to the y-axis, and it proves then that you can't do that. You'll never draw to the y-axis. You always find the acute angle created by the terminating ray and the x-axis. So, quadrant number one is I don't know why that's off center there, but quadrant number one is a trivial reference angle, meaning that if my angle theta, if theta is between 0 degrees and 90 degrees in Q1, then theta is the same as theta bar. The reference angle is the same as the angle of interest. So you really want to go through if I give you tell me a sine of 30, you don't have to go through this reference angle process that we're going to learn about here for that problem. Okay. So we'll jump straight to quadrant 2 here. Quadrant 2 is when theta is between 90 degrees and 180 degrees. Okay? Theta is between 90 and 180. If I say theta is 150 degrees, how many degrees is theta bar? 30. How'd you do that? Okay, so if I want to find theta bar in the second quadrant, it's going to be theta removed from 180. So 180 minus theta. In this case, yes, but theta bar is not by definition always a supplement. Okay, but in the second quadrant it is. The way I like to do it, and it's really the same approach, but I don't like using the formulas. I just know that this ray is rotating, kind of like if we come down to the GeoGebra. If we say we're at 150, and I want to know, well, how many more degrees do I need to get so that I'm here? Well, if I'm at 150, how many degrees is that red ray rotating? 30. Okay? So I always think about how many, I always want to get to this image right here, where I got a straight angle. Okay? So if my theta is there at 137, 138, okay, then I got to think, okay, well, I got to go then 42 degrees. I got to rotate 42 degrees through to get to that straight angle. Does that make sense? And that would be my reference angle. If I'm going down below, if I'm at 210, okay, I want to get back to the x-axis. Okay? I want to go the shortest angle back, or the smallest angle back to the x-axis. So if I'm at 210, to get the smallest degree back to the x-axis would be that there, right? Does that make sense? So if I'm at 210, how many degrees do I need to go back? 30. So my reference angle here, if I'm at 210 in the third quadrant, would be 30. Well, how can I find, formula-wise, if my angle is 210, how can I find that 30 formula-wise? Okay, so I'm going to draw that. leg of that right triangle, and that's what the direction said. So the reference angle is created by taking the terminal ray, a point on the terminal ray, and drawing a line back to the x-axis. Okay, and this would be that angle. So if this is 210, how do I get that to be 30? Where's 210 minus 180? So in this case, if I'm in the third quadrant, where we have an angle that is between 180 and 270, okay, your formula for theta bar is going to be theta minus 180. So that's where we're saying that theta is not always, or theta bar is not always the supplement of theta. Okay. The next thing to talk about, I think, here is, those are differing formulas. In quadrant 2, it's 180 minus theta, and in quadrant 3, it's theta minus 180. People get those mixed up. The one thing that I want to make sure you understand is a reference angle. We're always going to use a positive theta bar. Okay? We always want theta to be positive. So could I augment those two and say quadrant 2 and quadrant 3 could be rewritten as just theta bar as the absolute value of maybe 180 minus theta, or theta minus 180? Either route would go. Because those two things, I'm going to get the same thing, right? Okay. But if I go 180 minus theta, because subtraction is not commutative, that might be positive, and then theta minus 180 might be negative, or vice versa. So if I take the absolute value, they're always going to be positive, and that would be okay. Okay, so that's maybe some way that you can change that formula a little bit to kind of meet your needs. If we're in the fourth quadrant, our theta is going to be a number between 270 degrees and 360 degrees, correct? 270 and 360. So if that is the case, between 270 and 360, then how do I draw that right angle, how do I find that theta bar? Let's say theta, do a specific example, is 330. How many degrees then would be this angle right there? 30, okay? Because you are looking for essentially the value that gets me to 360, right? From that 330. So the way that we're going to find theta bar here, and that's the way I always envision. Okay, I'm at 330 right now. This blue ray is at 330. How many degrees does it need to rotate to get to the positive x-axis to give me that straight angle? I need to go 30 degrees. Okay, or how do I get to 360? I need to go 30. But formula-wise, you can take 360 minus theta, and that will give you theta bar. And that's quadrant 4. Okay, so as we go through, if you're a person that is a formula-minded person and wants to use those, I am more of a visual type learner, so I think it's easier for me to say, okay, if I'm at 280 degrees, how many more degrees do I need to rotate to get to 360? Okay, well, I got to rotate, 90 degrees or 80 degrees. Okay, so that's the way that we're going to do that and find those reference angles. Now, and this is going to be maybe throw a wrench into things, because we haven't talked about this in a couple sessions, several sessions. But theta can be represented in radians as well. Okay, so we might be looking at that. Therefore, still we would have theta equaling theta bar in that case. Okay, but if we're in the second quadrant, we'd be looking at pi over 2 is less than theta is less than pi. And then theta bar would be pi minus theta. And then over here, in quadrant 3, we'd be looking at an angle between pi and 3 pi over 2. And theta bar would be theta minus pi. And then quadrant 4, we'd be looking at an angle theta between 3 pi over 2 and 2 pi. So theta bar would be 2 pi minus theta. Remember, pi radians is equal to 180 degrees. Okay? So at any juncture throughout the course, if you struggle, if it's in radians and you're struggling with that concept, you can use that conversion to make it go over to degrees, work it in degrees, and then come back at the end and convert it back to radians. Okay? I don't think that's efficient. Okay? So as we go through things, we'll do a couple questions that allow us to do that, demonstrate that. But if you're a person that says, I'm going to do that every single time, I'm not going to worry about learning these radian measurements and their equivalencies in degrees, and I'm just going to always use this conversion factor. You will find that if you do that, you are going to run out of time and only be able to finish about half of your test questions. Okay, so it's just something to keep in mind as we move forward. Eventually, as we use them more and more, like these two numbers, 270 and 3 pi over 2, you're going to relate those much like you relate radical 4 and 2. Okay, you're going to know that they are synonymous with one another. Okay. Huh? Yep. So that's how we find reference angles. So what I want to do is go through a series of, I think, 3 examples here of just finding a reference angle. In your homework, it's going to say, here's the theta, find theta bar. And then it's going to do that for a handful of questions. And then it's going to get you to extend a little bit and say, okay, now that we know what theta bar looks like, let's go a little bit further and say, well, okay, well, what's the sign of theta if you know what theta bar is? So that's kind of where this is kind of going to materialize to as we move forward. So example here says find the reference angle for theta equals 5 pi over 3. Okay, let's do this 2 ways. Let's approach this as a person that does not like radians, does not like dealing with them. Okay, and right now you don't know this. You probably don't. Does anybody off the top of their head know 5 pi over 3 how many degrees that is? Exactly. Okay, in about 2-3 weeks, you'll all be able to rattle that off and tell me exactly that that's 300 degrees. Okay? But if I don't know that now, don't we have the ability to say, okay, theta is 5 pi over 3. 180 degrees is equal to pi radians. So if I do this, and we're doing this in the first section, pi's cancel. 3 and 180 cancel, give me 60. 5 times 60 is 300 degrees, right? Okay, so I'm actually going to work with theta being 300 instead. I always like to draw that. You don't need to. Okay, but like I said, I'm a visual person, so I want to draw a picture, a little quick sketch. Doesn't have to be great. Okay, but I know that 270 is right there, correct? Okay, multiply by 90. So 90, 180, those are my quadrantal angles. So 300 degrees is going to terminate maybe over here somewhere. Does that make sense? Because for 180 degrees is equal to pi radians. So that's my conversion factor then. So that red angle is theta. Okay. Theta bar is that blue angle right there. That's my reference angle, right? Okay, how big is that? 60 degrees. So theta bar, okay, and you can do it this way. You can say, well, that's a fourth quadrant angle. We have a formula that says if I have a fourth quadrant angle, then 360 minus theta is going to give me my theta bar. So 360 minus 300, 60 degrees. So theta bar is 60 degrees. Now here's the issue with working in degrees when the question was presented as working with radians. If I type 60 degrees in, web sign, on a test or a quiz, it's going to be wrong. Okay? If they start you with radians, they want answers in radians. Does that make sense? They start you in degrees. They want answers in degrees. So what do I have to do if this is 60 degrees? I have to unconvert it, right? So I basically just take that reciprocal and multiply again. 60 divides by 180 gives me 1/3. Or 180 divided by 60 gives me 1/3. So you get pi over 3. So 5 pi over 3 as an angle theta produces a reference angle theta bar of pi over 3. Does that make sense? Okay. Now, I think that's inefficient. And the reason I think that's inefficient is because you had to do some multiplication here in order to do your work. And then here, you really undid what you did up here. Does that make sense? I don't think that's efficient. So, show you how to do this with radians. If theta is 5 pi over 3, okay? Now, the discussion here is going to take a little bit longer than, what you would do if you're doing this by hand, okay? But if my theta is in radians, then my angle measurements, my quadrantal angles, okay, I say quadrantal angles, I'm talking about 0 degrees, 90, 180, and 270, okay? In radians, they are 0, and that one's pi, right? So halfway in between those would be pi over 2, correct? Halfway in between pi and 0, or a lot of times we'll put 2 pi down here on the bottom. Does that make sense? Halfway between pi and 2 pi is 3 over 2 pi. Does that make sense? Okay. So we put the quadrantal angle, we put everything in radians. Okay. Now, I don't know where 5 pi over 3 resides, where it terminates in the 4 quadrants here, because all my denominators are different right now. It's hard to compare things with different denominators, right? Okay. But if I'm able to make my denominators all the same, that would make my life a little bit easier. So, how can I rewrite 2 pi? And then like I said, this should be something that we can do pretty quickly on our own eventually. 2 pi, the same thing as 6 pi over 3. Good. Pi would be 3 pi over 3, correct? Okay, pi over 2. Okay, well, let's think about this. I don't like, so this would be 6 pi over 3 would also be 0 pi over 3, right? Okay, if I start at 0. I don't like changing a denominator of 2 to a denominator of 3 through multiplication. It was easy here. Basically, here all I do is multiply by 3 over 3, right? Okay. Over here, with pi, all I do is multiply by 3 over 3. Well, what do I need to multiply 2 by to make it 3? I don't want to have to think about that. Does that make sense? And then there's going to be a lot of problems where it might not be a 3 that I need to make. Maybe I need to make it a 5. Maybe I need to make it a 7. I don't want to do that every single time. Yeah, we're between 0 and 3. What is halfway between 0 and 3? 1.5. Okay, so can't I just write this? Now, we usually wouldn't do this in practice, but can I write that as 1.5 pi over 3? Does that make sense? Now, in all actuality, we'd probably would want to write it as like 3/2 pi over 3. But I don't want to do it that way, because 1.5 pi over 3 is going to be sufficient for us. Okay? Well, if that's 1.5 from 0 to there, then it's 1.5 from there to there, which would be 1.5 from here to there. Does that make sense? So doesn't this make this 4.5 pi over 3? And halfway between 3 and 6 is 4.5. Does that make sense, everybody? Just cutting things in half here. Okay? Why do I do that? Because now, can you see where theta of 5 pi over 3 would terminate? Do you see how far you'd have to go? You'd have to go beyond there, go beyond 3 pi over 3, go beyond here, but not too much further beyond there, right? Okay, because I'm at 4.5 when I'm right here, so I need to get to 5. Okay, so that theta would be 5.3, and this is one of the reasons why we used radians over degrees, because once everything is in the same denominator, now I'm just asking, how do I go from 5 pi to 6 pi? if I'm counting, I need to go by pi, right? 1 pi. Okay? But it's in thirds, so my theta bar would be pi over 3 here. That's exactly what we determined right here, wasn't it? Okay? Here's the thing. I'm not going to make you right now do things in radians. Okay? But the nature of the course, the nature of time constraints, the nature of being efficient will force you eventually to do things in radians. Okay? I will eventually do everything in radians. Degrees are going to slowly fade away. All right? Because radians are so much more natural, so much easier to work with once we get denominators to be the same. Okay? If I'm looking at this question here, okay, this is a reference angle doing it in degrees. Okay? Do I like an angle of 870 degrees? Why not? Yeah, it's too big, greater than 360. Okay? So if theta is greater than 360, you're going to subtract 360k, where k is an integer, until theta resides between 0 and 360. So if k is an integer, it means it's going to be 1, 2, 3, 4, whatever. Basically what that says is that you're going to subtract multiples of 360 until you get a sum that is between 0 and 360. So I like to use especially when these numbers are a lot bigger, 860, you're not going to really see it happen, but if I go 860 minus 360, that is 860, right? 870. 870 minus 360, it gives me 510. So that would have been when k was 1. So I don't want to subtract just 360, right? So then we make k 2, and I subtract another 360. 150. And I'm going to stop right there because there's 150 between 0 and 360. Okay. So theta equaling 870 is coterminal with theta of 150. Okay. Now that's not my reference angle. That's just a coterminal angle with 870. Does that make sense? So this whole process is, don't like 870 or 870. Let's look at a number that is going to generate the same information, 150. But we don't like 150. So now we're going to find a reference angle that's going to generate everything we need to know about 150. Is that okay? Now, if you had a question like this where it was like 1540. If theta was 1540, I can go minus 360. Desmos does this as well, but gives me that. I was going to hit minus 360 again. Obviously, it doesn't give me what I'm looking for yet, right? But now because it says A and S minus 360, if I hit enter, it's going to copy and paste this. But then when it sees A and S in this next line, it's actually going to refer to 820. So it's going to continually subtract 360 for me when I hit enter. Does that make sense? It'd just be a little bit more efficient or quicker way for you guys to use your calculator. Like I said, I think Desmos does that. I don't know if you'll use that enough to create or write a little bit of a program in Desmos that would help with that. Let's see if I go to for G, or not G, the graphing tool in Desmos, and I just say, let's say we got like 1540. I'm going to say minus 360K. It says add slider for K, so I'll do that. But I'm going to keep my step at 1. And then I'm going to just start subtracting. I'm going to start moving this slider here, and you see how it starts subtracting multiples of 360. And I just stop my slider when it gets between 0 and 360. So you could do it that way. But like I said, I don't know if you're going to, maybe there might be one assignment where we have 10 of those in it or something like that, and that would be maybe the only assignment that you see an abundance of those, that writing a program would make sense. You can do the same thing with Excel. Okay. So 150 is what we're going to deal with. So now if I go draw my 150. Well, let's do this real quick. Let's draw the 870. So 870, so there would be 360 degrees. There would be 720 degrees. And then there would be 870. Does that make sense? Okay. Well, if I look at 150, 150 is just going to be right there. Do they or maybe it's a little bit further, but do they terminate at the same spot? Yeah. Okay. But again, so that's theta equaling 870, theta equaling 150. I'm not saying that an 870 degree angle is the same as a 150 degree angle. If you stand up and I tell you do an 870, you're going to be a person that spins around 2 complete times and then another 150 degrees, right? If I tell person B do a 150, you're not going to spin around 100 or 1 complete rotation, right? So person 1 is going to be dizzier than person 2, right? So they are different angles, but the knowledge that we know about 150 is going to tell me everything we need to know about 870, okay? Because they're coterminal. Now we don't like the 150 because it's bigger than 90. So we look at our reference angle, which is going to be this theta bar right here. How big would that angle be? Be 30 degrees, right? Okay. Now, 30 degrees, let's say we had a third person, I asked them to rotate 30 degrees. They would be obviously, if we put these 2 people back to back, they'd be looking right now in opposite directions of one another. Okay. But everything that we know about the person that rotated 30 degrees will tell me everything I need to know about the person rotating 150 degrees, except for the plus or minus aspect. Okay. So my reference angle here for 870 is 30 degrees. Okay. So if I told you, what is here's where we're getting at with this. If I ask you, what's the sine of 870? You're not going to want to do that. You're not going to have that knowledge. Okay. So then you say, well, I'm not going to say 870. What's the sine of 150? And you say, well, I don't have that knowledge either. So what's the sine of 30? Does anybody know what the sine of 30 is? Sine of 30 is 1/2. Why is the sine of 30 1/2? It's because if this is 30 degrees, that's in and that's 2 in. Sine is opposite of hypotenuse, right? So sine of 30 is 1/2. Sine of 150 must then be what? 1/2. Sine of 870 then must be what? 1/2. Sine of 870. 870 stops in the second quadrant, right? All students take calculus. Sine in the second quadrant is sine's y divided by r. What would be the y value of a point on this right here? Wouldn't that be a positive? So sine is positive. So all students take calculus. Those letters are telling you which ones are positive in those quadrants. So 1/2, right? So let's take our calculator real quick and see. And as we see enough of these, obviously, I get you, we're not proficient. It's day 1 seeing this, day 2 seeing this. Eventually, you're going to be quicker at doing that than grabbing your calculator, turning on, changing the mode, typing in 870. Okay? If I type in sine of 870, 0.5. Okay? Does that make sense? Now, if we were in radians, instead of subtracting, so let's go 27 pi over 4. Let's say that is my theta. Okay. Instead of subtracting 360, we're going to subtract what? 2 pi. Okay. So we're going to subtract, to find theta bar, we subtract 2 pi k, where k is an integer, until theta comes between 0 and 2 pi. Okay. Now, here's the issue. With fractions, subtracting fractions stinks if the fractions don't have a what? Common denominator. So I'm not going to use 2 pi in that format. Because my denominator here is 4, I'm going to subtract 8 pi over 4. Okay? I'm going to subtract 8 pi over 4, because now it's just a matter, because the denominators are the same. That's still 2 pi. But now because the denominators are the same, all I have to do is the mental math is 27 minus 8. Right? Now, it's 27 minus 8. Does that give me between 0 and 8 pi over 4? Because now this changes this. I want to stop subtracting once I get theta between 0 and 8 pi over 4. Well, if I take 27 minus 8, do I get something between 0 and 8? No, I get what, 19? So subtract 8 again, I get 11. So I subtract 8 again, and I get 3. Now I stop at 3 because that's between 0 and 8, right? So ultimately, we subtracted 3 revolutions around our circle. Okay, we subtracted a total of 24 pi over 4s, right? That's another way of thinking about it. And people say, okay, well, if this is 8 pi, what is the greatest multiple of 8 that will be less than 27? Does that make sense? And that's 24. So I subtract 24 pi over 4. So that's going to give me theta bar to be 3 pi over 4. Nope, I'm sorry. That's going to be theta to be 3 pi over 4. Okay, that's a coterminal angle with 27 pi over 4. Okay, reference angle. Well, if this is 0, this is 8 pi over 4. This would have been 4 pi over 4 because that's just pi. This is 6 pi over 4. This is 2 pi over 4. Does that make sense? Still pi over 2, right? Still pi, still 3 pi over 2. But now 3 pi over 4, it's just looking at that number compared to that number, so 3 must be halfway between, right? So there's my theta of 3 pi over 4. It's the same location that 27 pi over 4 would be, so then it generates the exact same theta bar right there. What's that theta bar going to be? This is 3 pi over 4. How much do I need to go to get to 4 pi over 4? Pi over 4. So everything I need to know about 27 pi over 4 will be the exact same thing I need to know about pi over 4, except for the plus or minus aspect. So real quick, let's do 2 minutes here, 3 minutes. Do one extension of this. So say find sine of 240. This is the purpose of finding reference angles. Sine of 240. I don't like 240, right? So what we're going to do, we know 180 is there, we know 270 is there. That gives us an idea of where 240 should terminate, right there, correct? Okay, that's theta. What is theta bar right here? If you're for a formula person, we can go theta bar equals theta minus 180 because we're in the third quadrant. So 60. So theta bar is 60 degrees. Okay? Meaning then, I could look at an angle in the first quadrant where it's 60 degrees. Does that make sense? That 60 degree angle is exactly the same thing as if I were to extend this ray, this terminating ray, as an opposite ray. That's the 60 degree angle right there. Aren't those vertical? Okay. So now if this is 60, this is n radical 3, this is 2n, this is n. Okay? So when I want to know sine of 240, I'm actually going to ask, what is the sine of 60? Because the sine of 60 is going to be n radical 3 over 2, right? Or 2n. And that's going to reduce to radical 3 over 2, correct? So sine of 240 numerically is going to have the same as the sine of 60. It's going to be radical 3 over 2. But all students take calculus. Tangent is the only one in the third quadrant that is positive. 240 is third quadrant, right? So sine of 240, negative radical 3 over 2. So the reference angle stuff is going to give us the numerical quantity, radical 3 over 2. Then knowing what quadrant my angle terminated in is going to give me the plus or the minus aspect of that number. Okay? Does that kind of make sense? So what this is going to allow us to do, think about if we had no technology. We could determine any angle from 0 to infinity by knowing any angle from 0 to 90. That's what this is going to do for us. Does that make sense? Okay? And what we're really going to like about this is that obviously we don't want to talk about any angle from 0 to infinity because there's so many of them. We like to talk about multiples of 30. Any angle from 0 to infinity has a multiple of 30. We should be able to know its sine, cosine, and tangent by knowing the sine, cosine, tangent of 30, 60, and 90. Does that make sense? Eventually, then we'll have some formulas, some techniques that allow us to maybe find halves of those. So what's half of 40 or half of 90? 45. What's half of 30? 15. Okay? So we might be able to find, they're called half angle formulas. We'll be able to use the knowledge about 30, 60, 90 to find multiples of 15. So if I'm asking, what's the sine of a 75-degree angle? Well, that's a multiple of 15. We should be able to do that, okay, quickly without technology. Does that make sense? And we can use the technology to check that we've done it right. But the technology will never give us an exact answer. What we're doing here will always give us the Radical 3 or 2. Okay? And there's applications. I mean, at least technology that we currently, like, if you did a Google search, I would say that it's going to be rare for you to be able to find a calculator. You type in sine 240 and it spits back negative Radical 3 or 2. But there is technology out there that will do it, but it's probably pricey.